Hello everyone, this is Zhang from McGill University. The paper I'll present is called Physiological Pitch Range Estimation from a Brief Speech Input, a study on a bilingual parallel speech corpus. First part, Introduction. Pitch is crucial in speech communication, as speakers usually use it to convey a lot of important linguistic information like tone and intonation. Pitch perception has to rely on very efficient pitch normalization process. As shown in the figure, imagine there are two sounds from two different speakers, but they are at the same F0 level, shown by the two red lines. But in speaker 1's pitch range, it's representing a high pitch. In speaker 2's pitch range, it's representing a low pitch. So we never perceive the pitch height from the absolute F0 of the sound, but the relative height within the speaker's pitch range. Yes, we also perceive pitch height according to the context, but in this paper, we don't focus on the context effect. This kind of pitch normalization happens automatically and almost everywhere in speech communication, although we may never notice it. Besides, this normalization process is proved to be very efficient. It needs only 6 glottal periods. Previous studies indicated that during this efficient pitch normalization process, listeners are able to perceive the pitch range of the speaker. In other words, to precisely decode whether the speaker is producing a high or mid or low pitch, listeners have to know where is the upper and lower limits of the speaker's production, namely the pitch range. Different people use the word pitch range to represent different things. Basically, there are two subtypes of pitch range. One is called speaking pitch range. It varies with speaker's mood, speaking style, and language proficiency. The other is called physiological pitch range. It reflects the maximum range that a speaker could produce in speech communication and is determined by a speaker's organic factors and vocal characteristics. So it does not vary with speech communication. As we talked before, from a very brief speech, human beings could perceive the physiological pitch range instead of the speaking pitch range, so that they can normalize the pitch very efficiently. Obviously, from such a brief speech, there are insufficient F0 variation to cover the whole range of F0 of the speaker. So there must be other factors that helps people to perceive the pitch range, namely spectral information. Studies have shown that F1 minus F2 and spectral slope, this information could help people to perceive the pitch range. Based on these conclusions, in our previous study, we proposed a novel method of pitch range estimation. We used the LSTM model to imitate human beings' ability of the physiological pitch range estimation from the spectral feature of only 300 millisecond speech input. In the current study, as a following study, we have mainly two objectives. The first one is to modify and improve the previous model. The other one is to verify the proposal by comparing with the traditional method of pitch range calculation. The traditional pitch range calculation is also called long-term distributional method. Just calculate the maximum and minimum F0 value from all the available speech from a speaker. Next part, experiment. The improvement from the previous model contains three aspects. Firstly, we use more diverse speech corpora. There are 77.5 hours speech in total from 154 speakers from the following three corpora. Secondly, we modify the parameters describing the pitch range. In previous study, we use mean and standard deviation to describe the pitch range, because the pitch range could be represented by mean plus minus 2 times standard deviation. But we found that studies showed that the perceptual cues for ceiling and the floor are actually different, and the ceiling is inherently more dynamic than the floor. So in the current study, we use 3 separate parameters to represent the pitch range. As shown in the figure, we use ceiling and mean and floor to describe the pitch range. Thirdly, we also improve the training efficiency of the model. In previous study, we built separate model for each parameter, but in this study, we could train the 3 parameters together in a multitask method. As shown in the figure, the structure of the model contains 2 layers of LSTM. One is a shared hidden layer, the other is a separate hidden layer. The performance of the model is shown in the table. The evaluation method is mean absolute percentage error. From the table, we could find the performance of mean is improved from the baseline model, but we failed to find the performance of the other 2 parameters in the baseline model because of the different model designing. For more details about the experimental setup, you might check our previous study in 2018. Next, we verified the effectiveness of the proposal on a bilingual parallel corpus. According to previous study, a speaker's L1 and L2 speech have different speaking pitch ranges, but the same physiological pitch range. The proposed method, according to our claim, is estimating the physiological pitch range of a speaker, but the traditional LTD method is actually estimating the speaking pitch range of a speaker. So there is a hypothesis that for the same speaker, the proposed method would predict almost the same results from a speaker's L1 and L2 speech, but the traditional LTD method would give different results. And we happen to have such an corpus established in 2007. It's called the 301 speech corpus. There are 18 native Japanese speakers in total, and they are gender balanced. There are 301 parallel utterances of Japanese and Mandarin. So we choose 20 parallel sentences from them and divide it into 300 milliseconds chunks and test it under both of the 2 methods. Here are the results from the 2 methods. The upper figure shows the estimation results from the LTD method, and the lower figure shows the estimation results from the proposed method. The horizontal axis shows the language and the gender information of the speech input. Like C represents Chinese and J represents Japanese. Because all of the speakers are Japanese speakers, so Japanese is their L1 speech input and Japanese is their L2 speech input. And I'm and F represents the male and female speakers respectively. Let's take male speakers data as an example, shown by the middle 2 columns. In the upper figure, which is the LTD method, the estimation results from their L1 language and L2 language are actually different across all the 3 parameters. But the case is different in the proposed method, as we can find the results of the pitch range parameters from their L1 and L2 speech are almost the same. So And the case is pretty similar in the female speakers data, as well as the average data. To test whether the estimation results from the L1 and L2 input are significantly different in the two methods, we also carried paired samples t-test on the range of difference between the two methods. We firstly calculate the results difference between the two input, which is the L1 and L2 speech input, for the two methods and across all the parameters. As shown in the figure, in each of the parameters result, the p-value shows significant difference between the two methods, and the mean value is negative, which shows that the proposed method has less difference between the two input languages than the traditional method. So we can conclude that the proposed method has significantly less variability on the results of the same speaker than the traditional method. That is to say, the results has proved the hypothesis we mentioned before. Finally, we have the following discussions. According to previous studies, when limited speech input is available, spectral information helps allow to impeach perception. Based on this conclusion, we propose the method of pitch range estimation from brief speech input. Tested on a bilingual parallel speech corpus, the current study proved that the proposed method is able to estimate the physiological pitch range, other than the speaking pitch range, which is what the traditional method estimates. There are also some weaknesses in the study, especially the lack of the annotated label of the physiological pitch range in both of the model training and model evaluation process. In the future, if we could obtain the labels of the physiological pitch range of the speakers, the performance of the prediction model should behave better than the present one. Thanks for your listening. If you have any question, feel free to contact me at the following email address.